Welcome back to G Fun Facts Online. Today we are digging deep into the invisible infrastructure that holds our digital world together. For over 50 years, civilization has relied on a single material to transmit information: silica. Standard single-mode fiber has been the undisputed monarch of telecommunications. It is a marvel of materials science, a strand of ultra-pure glass doped with germanium, capable of trapping light, using total internal reflection and guiding it across ocean floors and continents. But glass, for all its purity, has a fundamental flaw. It is matter. When light travels through matter, it pays a tax. It slows down, trudging through silica at roughly 2/3 the speed of light in a vacuum. It scatters, colliding with microscopic fluctuations in the glass structure, a phenomenon known as Rayleigh scattering. And it distorts, succumbing to nonlinear effects when intensities get too high. For decades, engineers hit a wall. They had refined silica to its atomic limits, achieving attenuation rates of 0.14 decibels per kilometer. That number hadn't budged significantly since the 1980s. The glass ceiling had been reached. But then, a radical idea took hold. What if the best medium for transmitting light wasn't a better glass but no glass at all? This is the story of Hollow-Core Photonics, the technology that is breaking the speed limit of the internet and opening the door to a new era of quantum computing and artificial intelligence. To understand why hollow-core fiber is such a revolution, we first have to appreciate the physics of nothing. Light, by its nature, wants to spread out. In a standard optical fiber, we keep light trapped in the core by surrounding it with a cladding that has a lower refractive index. This bounces the light back in. But if you try to send a laser down a simple copper pipe, or a glass capillary filled with air, the light grazes the walls, gets absorbed, and dies out within centimeters. To trap light in an air core for kilometers requires tricking the photons. Over the last 30 years, scientists developed 3 distinct mechanisms to do this. The first breakthrough came in the 1990s with the photonic bandgap effect. Imagine a honeycomb lattice of air holes in glass surrounding a hollow core. This periodic structure acts like a crystal for photons. Just as a semiconductor crystal forbids electrons from having certain energies, this glass-air structure forbids light of certain wavelengths from existing in the cladding. When light tries to escape the core, it hits this forbidden zone and is forced back into the center. These fibers were the first to demonstrate true air guiding, but they had narrow bandwidths and high scattering loss. As research progressed, a more robust mechanism emerged, called anti-resonance. Instead of a crystal lattice, these fibers rely on the interference of light passing through thin glass membranes. Think of the thin glass wall surrounding the air core as a mirror. For specific wavelengths, the wall is transparent, but for others, the anti-resonant wavelengths, the glass wall acts as a highly perfect mirror, reflecting the light back into the air core. This is the anti-resonant hollow-core fiber. It offers enormous transmission windows, from the ultraviolet to the mid-infrared. But the modern champion of this technology is the nested anti-resonant nodeless fiber, or NANF. Early designs had points where glass tubes touched the outer cladding, creating nodes where light could leak out. The nodeless design fixed this by floating a ring of non-touching glass tubes inside the jacket. But light could still leak through the tubes themselves. The solution was nesting. By placing a smaller tube inside each outer tube, like a Russian doll, researchers created a second reflective barrier. If light tunnels through the first mirror, the second one catches it. This evolved into the double-nested anti-resonant nodeless fiber. In this geometry, less than 1 part in 10,000 of the optical power travels in the glass. The rest travels in pure air. This structure recently allowed researchers to achieve loss rates of 0.091 decibels per kilometer, shattering the fundamental limit of solid silica. The journey to that record was a winding path. It began in 1991 with Philip Russell, a professor at the University of Southampton. Bored during a conference talk, he sketched a honeycomb structure, wondering if photonic band gaps could work in fibers. That sketch led to the first holy fiber. By 1999, his team successfully guided light in a hollow core. It was a scientific marvel, but the losses were initially millions of times worse than standard fiber. The ensuing decades were known as the Loss Wars. 2 camps emerged. The PBG camp tried to perfect the honeycomb, while the Kagome camp explored anti-resonance. The turning point came around 2014, when Francesco Paletti and his team proposed the NANF structure. They predicted that simplified, non-touching tubes would decouple light from the noisy glass almost entirely. It took years to figure out the manufacturing, but by 2024, the prediction held true, and the useless curiosity beat the reigning champion of materials science. While the low loss is a scientific triumph, the speed of hollow-core fiber is what captivated the financial and computing industries. In standard glass, light travels at roughly 200,000 kilometers per second. In a hollow-core fiber, light travels through air at roughly 300,000 kilometers per second. This is a 47% speed increase. In terms of latency, This saves roughly 1.5 microseconds for every kilometer of cable. To a human, this is nothing. To a high-frequency trading algorithm, it is an eternity. Wall Street was the first adopter. Firms spent millions to shave off microseconds between Chicago and New York. A hollow-core link became the gold standard. But the niche trading market was just the proving ground. The explosive rise of artificial intelligence created a far larger demand. Modern AI models are trained on massive clusters of GPUs that act as a single supercomputer. These processors must constantly exchange vast amounts of data. If the network is slow, expensive GPUs sit idle. This is why Microsoft acquired Luminosity in 2022. They realized that to build the Azure supercomputers of the future, they needed to eliminate glass latency. By deploying hollow-core fibers to connect racks, Microsoft reduces the tail latency of training runs, making their AI clusters significantly more efficient. Beyond speed, hollow-core fibers possess superpowers that solid glass cannot emulate. First is the power of air. In solid fiber, high laser power heats the glass, leading to thermal failure or nonlinear distortion. In hollow-core fiber, the light travels through air, which is thousands of times less nonlinear. You can pump kilowatts of peak power through a hair-thin fiber without it overheating. This makes it ideal for industrial laser delivery, allowing flexible robots to wield ultra-short pulse lasers for precision manufacturing. Second is the full spectrum. Silica turns opaque in the mid-infrared and ultraviolet. But because hollow-core fiber guides light in a hole, the cladding material matters much less. This opens up the mid-infrared window, critical for chemical sensing and laser surgery. Manufacturing these fibers is a feat of engineering. It often starts with a stack-and-draw technique. Engineers hand-assemble a preform of glass tubes to create the nested geometry. This preform is heated to 2000 degrees Celsius and drawn into a thin thread. The nightmare is keeping the holes open. Surface tension wants to collapse the molten glass. To prevent this, manufacturers must pressurize the internal holes with inert gas during the draw. But the core needs one pressure, and the nesting tubes need another. It requires precise active control. Once made, splicing is another challenge. You cannot simply melt two ends together, or the holes will collapse. Solutions involve specialized low-temperature splicing or mechanical connectors. Hollow-core fiber is also a test tube. Because the core is empty, it can be filled with gas. By pumping methane or carbon dioxide into the core, the fiber becomes a highly sensitive sensor, detecting trace gases at parts per billion concentrations. In the realm of quantum computing, researchers are filling these fibers with alkali metal vapors like rubidium. When laser light interacts with these atoms inside the core, it generates Rydberg states, creating a room-temperature quantum memory or sensor inside a flexible cable. This helps miniaturize quantum computers. Furthermore, hollow-core fibers make excellent gyroscopes for navigation. Unlike solid glass, the refractive index of air barely changes with temperature, making these gyroscopes vastly more stable for submarines and aircraft. Commercially, the transition is underway. Luminosity, now part of Microsoft, leads in low-loss fiber. OFS and NKT photonics are pushing industrial and scientific applications. Giants like Corning and Heraeus have awoken, partnering to scale manufacturing. Even Chinese manufacturers have announced record-breaking deployments, signaling a geopolitical tech race. Will hollow-core fiber replace all fiber? Probably not. It is expensive to make. Standard glass is cheap and sufficient for bringing the internet to your home. However, hollow-core will likely become the standard for data center interconnects, backbone networks between cities, and potentially future transoceanic cables. The physics is settled. We are witnessing a fundamental shift. For 50 years, we optimized the glass. Now we are removing it. Hollow-Core Photonics combines the speed of radio waves with the bandwidth of fiber optics. As we lay thousands of kilometers of these hollow threads to power AI and quantum technologies, we prove that sometimes the best material is no material at all. The future of light is empty, and it is faster than ever. That wraps up this deep dive into the technology shaping our future. Thanks for listening to G Fun Facts Online.